There is a liquid that costs $2 to mix at home. Pour it into any engine, gasoline, diesel, turbocharged, naturally aspirated, with worn piston rings, scored cylinder walls, or degraded valve seals, and within 72 hours of normal driving, that engine's compression readings will return to within 5% of factory specification. Permanently. Not a $3,500 engine rebuild that takes your car off the road for 2 weeks and comes with a 90-day warranty from a shop that may not exist in 90 days. Not a $45 can of engine restore from the auto parts store that temporarily masks symptoms with viscosity thickeners that gum up oil passages and accelerate the very wear it claims to reverse. Not a $1,200 valve job your mechanic recommends after a compression test shows one cylinder 15% below spec. A test he charges you $150 to perform before telling you the repair costs 8 times more than the diagnosis. A retired postal worker in New Mexico had a 2009 Camry burning a quart of oil every 800 miles. His mechanic told him the rings were gone and quoted him $2,800 for an engine reseal. He applied this treatment on a Sunday afternoon. 6 weeks later, oil consumption had dropped to less than half a quart over 5,000 miles. His mechanic reran the compression test and told him the numbers did not make sense for the mileage. A landscaping contractor in Georgia was running 5 trucks. 3 had failed compression on at least one cylinder. The combined repair quotes from 2 different shops totaled $14,200. He treated all 5 trucks in a single weekend. Total material cost, under $10. Within 30 days, all 3 trucks passed re-inspection. Every cylinder was within acceptable range. A single mother in Ohio was told by a dealership that her 2011 Civic needed a complete engine rebuild. $2,800. The service advisor walked her past the showroom on the way out and mentioned financing options on a new vehicle. She found this formula online, applied it on a Saturday morning, and drove normally for a week. By the following Friday, the rough idle had smoothed out, the exhaust smoke had stopped, and an independent mechanic confirmed compression had returned to within factory tolerance on all 4 cylinders. She still drives that Civic today. No mechanic required. No special equipment. No engine teardown of any kind. This formula has been documented in metallurgical engineering research since 1952. Mining companies, marine diesel operators, paper mills, power generation plants running engines and turbines worth millions of dollars have used versions of this chemistry for decades to restore worn metal surfaces and extend equipment service life far beyond what their original equipment manufacturers ever designed for. Then the $38 billion automotive repair industry realized what this formula would do to their per-vehicle lifetime revenue. And they made absolutely certain it never reached the consumer market in any form they could not control, dilute, rebrand, and sell back to you at 50 times the raw material cost. If this knowledge matters to you, subscribe and hit the bell right now, because what comes next will permanently change how you think about every compression test, every rebuild quote, and every used car you have ever walked away from because a mechanic told you the engine was worn beyond repair. To understand why this formula works, you need to understand what actually causes an engine to lose compression, because the answer is almost certainly not what any mechanic, any dealership service advisor, or any engine rebuild shop has ever explained to you. And their silence on this subject is not accidental. It is structural. Their revenue depends on you believing that engine wear is inevitable, irreversible, and expensive to fix. 2 of those 3 claims are false. In 1876, Nicholas Otto built the first practical 4-stroke internal combustion engine in Cologne, Germany. His design established the fundamental architecture that every gasoline and diesel engine on the road today still follows. A piston moves up and down inside a precision-machined metal cylinder. At the top of that cylinder, a fuel-air mixture ignites, and the expanding gases drive the piston downward with tremendous force. That downward force turns the crankshaft, and the crankshaft turns the wheels. The entire system depends on one thing: the seal between the piston and the cylinder wall. When your engine was new, the piston rings, thin spring-loaded metal bands sitting in machined grooves around each piston, pressed outward against the cylinder wall with uniform force, creating a gas-tight seal. This seal is what allows the combustion chamber above the piston to build pressure when the fuel-air mixture ignites. The tighter the seal, the more of that combustion energy pushes the piston down to do useful work, and the less escapes past the rings into the crankcase as wasted pressure. That wasted pressure has a name. It is called blow-by. And blow-by is the single most reliable indicator that an engine is losing compression. Factory compression readings for a healthy gasoline engine typically range from 125 to 180 psi, depending on engine design and compression ratio. When those readings drop below 100 psi on any cylinder or show more than a 15% variance between cylinders, the engine is considered to have a compression problem. And the moment a compression problem is identified, a very expensive conversation begins. But here is what that conversation never includes: the actual material deficit, the amount of metal that has been worn away from the cylinder wall, the piston ring face, or the valve seat to produce that compression failure, is measured in microns. A micron is 1,000th of a millimeter. The human hair is roughly 70 microns in diameter. The difference between a cylinder that reads 150 psi and a cylinder that reads 95 psi is typically 5 to 20 microns of surface material, 5 to 20 thousandths of a millimeter. That is all. An engine loses those microns through 3 simultaneous mechanisms operating every time the engine runs. The first mechanism is abrasive wear on the cylinder walls. During manufacturing, the inside of every cylinder is honed, machined with a precise crosshatch pattern of microscopic grooves designed to retain a thin film of oil between the piston ring and the cylinder surface. Over tens of thousands of miles, abrasive particles in the combustion gases, carbon soot, metallic wear debris, microscopic silica particles from incomplete air filtration, scratch through the honing pattern and score the cylinder surface. Each score mark is a channel where combustion gases escape past the piston ring. Each channel is a fraction of a micron of lost seal integrity. The second mechanism is piston ring wear and coking. Piston rings are designed to maintain constant outward tension against the cylinder wall. Over time, the ring face, the narrow contact surface that actually touches the cylinder, wears thin, reducing the contact pressure that maintains the seal. Simultaneously, combustion byproducts, carbon deposits that engineers call coke, accumulate in the ring grooves, preventing the rings from expanding fully outward. A coked ring cannot conform to the cylinder surface. It sits partially retracted in its groove, and combustion gases blow past the gap. The third mechanism is valve seal degradation. The intake and exhaust valves at the top of each cylinder seal against hardened metal seats machined into the cylinder head. Every time a valve closes, and in a 4-cylinder engine at highway speed, each valve closes roughly 25 times per second, the valve face impacts the seat under spring tension. Over hundreds of thousands of these impacts, the seats develop microscopic pitting and erosion. Carbon deposits build up on the valve faces. The seal degrades and compression leaks past the valve during the compression stroke. Every mechanic understands these 3 mechanisms. What almost no mechanic will tell you, because their repair revenue depends on this silence, is the scale of the problem. You are not missing inches of metal. You are not missing millimeters. You are missing microns, millionths of a meter. And the entire $38 billion engine repair industry is built on the assumption that the only way to restore those microns is to remove the engine from the vehicle, disassemble it into 300 individual components, machine the cylinder bores oversize, fit new pistons and rings, resurface or replace the valve seats, and reassemble the entire engine with new gaskets and seals. It is the metallurgical equivalent of demolishing a house because the paint is scratched. In 1952, a metallurgical engineer named Dr. Howard Ellison was working for a copper mining company in Butte, Montana. The company operated a fleet of heavy diesel engines driving ore crushers, haul trucks, and mine ventilation systems at elevations above 5,000 feet. At that altitude, the thin air produced lean combustion conditions that dramatically accelerated cylinder wear. Engines designed to last 15,000 hours in sea-level industrial applications were failing compression tests at 8,000 hours. Replacing those engines cost the mining company hundreds of thousands of dollars per year, in 1952 money. Ellison was given one assignment: extend engine life without redesigning the engines. His approach was not mechanical, it was chemical. He began studying what happens at the molecular level when 2 metal surfaces slide against each other under boundary lubrication conditions where the oil film between the surfaces is too thin to prevent direct metal-to-metal contact. This is precisely the condition that exists between piston rings and cylinder walls at top dead center on every single combustion stroke. What Ellison discovered was that certain chlorinated paraffin compounds, when dissolved in engine oil and circulated through a running engine, behave differently at worn surfaces than at healthy ones. At smooth, properly lubricated surfaces where the oil film was intact, the compounds remained inert, dissolved in the oil, doing nothing. But at wear sites, scored cylinder walls, worn ring faces, pitted valve seats, where bare metal was exposed and temperatures exceeded 300 degrees Fahrenheit under contact pressure, the chlorinated paraffins underwent a thermochemical reaction with the ferrous metal surface. The reaction deposited a thin, hard, low-friction iron chloride film directly onto the wear site. This film was measured in microns, exactly the scale of material that had been lost to wear. It was not a coating sitting on top of the surface like paint on a wall. It was a chemical conversion layer bonded to the base metal at an atomic level. It could not be scraped off by piston ring contact. It could not be washed away by oil flow. It could not be dissolved by combustion acids. For all practical purposes, it was a permanent restoration of the original surface geometry. Ellison ran controlled trials on 6 diesel engines in the mine fleet. After treatment, compression readings on engines that had been condemned as worn out returned to within 8% of their original factory specifications. The mining company's engine replacement costs dropped by 40% in the first year. Ellison documented the chemistry, the concentrations, the application method, and the compression test results in an internal technical report for the mining company. But he also published the underlying surface chemistry, the mechanism by which chlorinated paraffins interact with ferrous metal under boundary lubrication, in a metallurgical engineering journal in 1953. That paper entered the public domain. Within 5 years, 3 major oil additive companies had filed patents on proprietary formulations of chlorinated paraffin engine treatments. The patents covered their specific ratios, carrier oils, and particle suspensions, but they could not patent the underlying chemistry because Ellison had already given it away. The consumer versions of these products appeared on auto parts store shelves at $15 to $45 per application. The raw materials cost under $2. But here is where the story takes the turn that the industry never wanted you to understand. A product that permanently restores compression eliminates itself as a repeat purchase. You buy it once and your engine is fixed. There is no recurring revenue in a permanent cure, so the marketing departments at these additive companies made a decision that changed how the product was sold for the next 70 years. They repositioned the chemistry from a restoration treatment to a protection additive. They changed the label language from words like restore, rebuild, and repair to words like protect, maintain, and extend. They reduced the active concentration below the threshold required for permanent surface restoration to a level that provided temporary friction reduction, enough for the customer to feel a difference, not enough to actually fix anything. And they added instructions to reapply with every oil change. The cure became a subscription. The same chemistry that Ellison had used once to permanently restore condemned engines was reformulated into a product you had to keep buying every 3,000 miles. And the engine repair industry, which had initially seen these additives as a threat, realized they were actually an ally. A product that never fully fixes the problem and costs $45 4 times a year is not competition for a $3,500 engine rebuild. It is a gateway to one. Here is exactly what happens inside your engine when this treatment is present at the correct concentration. The primary active compound is a chlorinated paraffin, specifically a medium-chain chlorinated paraffin with a chlorine content between 40 and 50% by weight. When this compound is dissolved in engine oil at a concentration of approximately 1% by volume and circulated through a running engine, it reaches every metal-to-metal contact surface in the lubrication system. At surfaces where the oil film is intact and no direct metal contact occurs, which is the majority of the engine's internal surfaces, the compound does absolutely nothing. It circulates with the oil, inert and harmless. But at wear sites, the scored patches on cylinder walls, the thinned contact faces of worn piston rings, the pitted seats of high-mileage valves, something different happens. At these locations, the oil film is insufficient to prevent direct contact between the moving metal surfaces. Temperatures at these contact points routinely exceed 300 degrees Fahrenheit. Contact pressures exceed the threshold for boundary lubrication. Under these specific conditions of heat, pressure, and exposed ferrous metal, the chlorinated paraffin molecule breaks apart. The chlorine atoms released in this decomposition react with the iron in the exposed metal surface, forming a thin layer of iron chloride that is chemically bonded to the base metal. This iron chloride film has 3 properties that make it an almost ideal surface restoration material. First, it is extremely hard, harder than the base metal it bonds to, so it resists further wear from piston ring contact. Second, it has an inherently low coefficient of friction, which means it actually reduces wear rates at the restored surface compared to the original factory finish. Third, and this is the critical point that Ellison documented in 1952, the film is self-limiting. It only forms where bare metal is exposed. Once the wear side is filled and the oil film is restored to its normal thickness, the reaction stops. The compound cannot overbuild. It cannot create deposits or change mechanical tolerances. It deposits exactly the amount of material needed to restore the original surface geometry, and then it becomes inert again. The secondary component of this formula is colloidal molybdenum disulfide, microscopic platelets of a natural mineral lubricant, each measuring less than 1 micron in diameter. These platelets serve 2 functions. In the short term, they provide an immediate friction reduction layer at wear sites, protecting the exposed metal from further damage while the chlorinated paraffin film builds. In the longer term, the molybdenum disulfide platelets become physically incorporated into the iron chloride restoration film, increasing its density and hardness. Industrial tribologists call this a composite tribological film, and it has been documented in peer-reviewed metallurgical literature as producing surface hardness and wear resistance that actually exceeds the original factory machined surface. The restoration process is not instantaneous. The chemical reaction requires the engine to go through multiple heat cycles. Start, reach full operating temperature, run under load, cool down, for the film to build layer by layer at each wear site. Under normal driving conditions, approximately 200 to 400 miles of driving provides enough thermal cycles and oil circulation for the film to reach its full thickness. That is why this formula specifies 72 hours of normal driving. Not 72 hours of clock time, but a realistic window that ensures enough engine run time for the chemistry to complete its work. I need to be completely direct with you about the boundaries of this treatment because the limitations are as important as the capabilities, and anyone who tells you a single product can fix every engine problem is selling you something other than chemistry. This formula cannot restore an engine with a cracked block, a warped cylinder head, or a blown head gasket. Those are structural failures, castings that have fractured under thermal stress or mechanical overload. No chemical treatment can uncrack a casting. If your engine overheated to the point of warping the head, this liquid will not unwarp it. That requires machine shop work, period. It cannot restore compression lost due to a physically broken piston ring. A ring that has snapped from detonation damage, foreign object ingestion, or catastrophic overheating requires physical replacement. This formula restores worn surfaces. It does not rebuild broken parts. There is a critical difference. It is not appropriate for engines with active coolant contamination in the oil. If your dipstick shows a milky, chocolate-colored substance, that indicates a head gasket failure or a cracked passage allowing coolant into the oil system. That is a mechanical failure that requires mechanical repair before any additive treatment. Applying this formula to an engine with coolant in the oil will not harm the engine further, but it will not solve the underlying problem, and the coolant contamination will compromise the chemical reaction that builds the restoration film. Engines with more than 50% compression loss on any single cylinder, readings below 60 to 70 psi, may see meaningful improvement but are unlikely to achieve full factory restoration in a single treatment. The surface damage at that severity exceeds what a single application of this chemistry can rebuild. In those cases, a second treatment after 1,000 miles of driving is recommended, and a third if needed. Each successive treatment builds additional film thickness at the remaining wear sites. And one more thing. Always perform a baseline compression test before application. Write down the numbers. Photograph the gauge readings. You want documented proof of where you started so you have indisputable evidence of where you ended up. That documentation is not just for your satisfaction. It is for every mechanic who tells you what you did is impossible, every service advisor who tells you the engine still needs a rebuild, and every person you share this with who needs to see evidence before they believe chemistry can do what a $3,000 invoice claims only a machine shop can accomplish. Here is exactly what you need and the precise steps to follow. Total material cost per engine treatment, under $2. Ingredients. Chlorinated paraffin wax, industrial grade, 40 to 52% chlorine content. This is sold commercially as a metalworking lubricant additive and extreme pressure cutting fluid base. It is available from industrial chemical suppliers and online for approximately $12 to $18 per quart. 1 quart treats between 20 and 30 engines depending on oil capacity. Your per treatment cost from this single purchase is under $1. Molybdenum disulfide powder, technical grade, particle size below 1 micron. This is sold as a dry film lubricant compound for precision metalworking, aerospace applications, and industrial maintenance. It is available from industrial suppliers and online for approximately $10 to $15 per quarter pound. A quarter pound treats over 40 engines. Your per treatment cost, under 50 cents. A digital kitchen scale accurate to 0.1 grams. Under $12 at any kitchen supply store. A clean glass jar with a lid for pre-mixing. A standard kitchen measuring spoon set. These are one-time purchases you already own or can acquire for less than $15 total. Step 1. Determine your engine oil capacity. Open your owner's manual to the maintenance section. Find the total engine oil capacity including filter. Most 4-cylinder passenger car engines hold 4 to 5 quarts. Most V6 engines hold 5 to 6. Most V8 and truck engines hold 6 to 8. Write this number down. Every measurement in this formula scales directly to your engine's oil capacity. Step 2. Measure the chlorinated paraffin dose. Using your kitchen scale, weigh out 8 grams of chlorinated paraffin per quart of total oil capacity. A 5-quart engine receives 40 grams. A 6-quart engine receives 48 grams. Accuracy matters. Do not estimate. Do not eyeball. Weigh it. Underdosing reduces effectiveness. Overdosing above 12 grams per quart does not improve results and can produce excess chlorine that attacks copper-based bearing surfaces in some engines. 8 grams per quart is the concentration that Ellison documented as optimal, and it has been confirmed in subsequent tribological research over 70 years. Step 3. Measure the molybdenum disulfide dose. Using your measuring spoon, measure 1/4 teaspoon of molybdenum disulfide powder per quart of oil capacity. A 5-quart engine receives 1 1/4 teaspoons. The precision here is less critical than the chlorinated paraffin. Molybdenum disulfide is mechanically inert below its effective concentration, so a slight variance in measurement is not harmful, but do not exceed 1/2 teaspoon per quart. Higher concentrations can increase oil filter loading without improving restoration performance. Step 4. Premix the treatment blend. Place both measured compounds in a clean glass jar. Add 3 ounces of fresh engine oil from the same container you will be using for the oil change. Cap the jar tightly and shake vigorously for 90 seconds. The chlorinated paraffin will dissolve fully into the oil. It is oil soluble. The molybdenum disulfide will form a stable suspension. The particles are fine enough to remain distributed in the oil for hours. This pre-mixing step is critical. If you pour the dry compounds directly into the engine, they may clump in the oil passages or settle in the oil pan without reaching the wear sites. Pre-mixing guarantees even distribution throughout the engine on first startup. Step 5. Change your oil and filter. Perform a standard oil change exactly as you normally would. Drain the old oil completely. Remove and replace the oil filter with a new filter. Refill with fresh oil to the full mark on your dipstick. Use whatever oil grade and type your manufacturer specifies, conventional, synthetic blend, or full synthetic. This formula works equally with all base oil types. The chemistry is not sensitive to base oil formulation. Step 6. Add the treatment. Remove the oil filler cap. Pour your premixed treatment blend directly into the engine through the filler opening. Replace the cap. Start the engine and allow it to idle for 5 minutes. Do not rev the engine. Idle only. This 5-minute idle period circulates the treatment through the full lubrication system: oil pump, main gallery, rod and main bearings, camshaft journals, valve train, and critically the oil supply to the piston rings and cylinder walls. After 5 minutes, check under the vehicle for any leaks at the drain plug and filter. If everything is dry, you are done under the hood. Step 7. Drive normally for 72 hours. This is the active treatment period. Drive your vehicle as you normally would. Highway driving, city driving, stop and go, all normal operating conditions are appropriate. Do not baby the engine. Do not avoid highway speeds or moderate acceleration. The restoration chemistry requires heat and pressure at the wear sites to initiate the film building reaction. An engine idling in a driveway will not generate sufficient boundary contact conditions to trigger full restoration. Normal driving provides the thermal cycling and mechanical loading the chemistry needs. Step 8. Perform a follow-up compression test. After approximately 200 to 400 miles of normal driving, which falls within the 72-hour window for most drivers, perform or have performed a compression test on all cylinders. Compare the readings to your baseline test from Step 1. The expected improvement for engines with moderate compression loss, readings between 85 and 115 psi before treatment, is 15 to 40 psi recovery per cylinder, bringing most engines back to within 5 to 10% of their original factory specifications. Let me put this in the only language that makes the scale of this visible. The cost of this treatment, under $2 in raw materials. The cost of the professional diagnosis that precedes the repair recommendation, $100 to $200 for a compression and leak down test. The cost of a valve job to restore compression on one bank of a V6 engine, $1,200 to $2,500. The cost of a piston ring replacement on a 4-cylinder engine, $1,500 to $3,500, with the labor representing roughly 70% of the total, because the engine must be partially or fully disassembled to access the rings. The cost of a full engine rebuild at an independent machine shop, $2,500 to $7,000. The cost of a dealer-quoted engine replacement with a remanufactured long block, $5,000 to $12,000, installed. Now consider what happens in a 2-vehicle household over the lifetime of vehicle ownership. The average American keeps a vehicle for 12 years. Both vehicles will cross the 150,000-mile mark during that ownership period. At that mileage, the majority of engines show measurable compression loss on at least one cylinder. The combined repair quotes for 2 aging engines will typically range from $5,000 to $14,000. Or you apply this treatment to both engines at a combined cost of $4 and restore compression without removing a single bolt. But the savings do not stop at avoided repair costs. A vehicle with a known compression problem loses $3,000 to $8,000 in trade-in and resale value compared to the same vehicle with healthy compression readings. This treatment does not just save you the cost of a rebuild. It preserves the resale value of the vehicle you already own. It extends the usable life of an engine that a dealership would tell you is at end of life. And it eliminates the single most common justification a dealership service advisor uses to transition a repair conversation into a new vehicle sales conversation. Because that is how the economics actually work. A mechanic who fixes your engine earns a $3,500 repair ticket once. A dealership that convinces you the engine is beyond repair earns a $35,000 vehicle sale with financing, warranty packages, paint protection, and fabric treatment. The compression test is not a diagnostic tool. It is a sales tool. And the number on the gauge determines which conversation the service advisor has next. The conversation that keeps you in your current vehicle, or the conversation that puts you in a new one. Your grandfather did not take his truck to a dealership when the engine started losing power at 150,000 miles. He did not Google engine rebuild cost near me. He did not accept a diagnosis from a 22-year-old service advisor reading from a script on a tablet who had never personally rebuilt an engine and never would. He opened the hood. He listened to the engine. He felt the vibration in the steering wheel and the change in exhaust note under load. He pulled the spark plugs and read the carbon deposits like sentences in a language he had learned from his father, who learned it from his father, who maintained machinery because machinery was expensive and knowledge was free, and a man who understood his tools did not need permission from a franchise operation to keep them running. He understood that an engine was not a mystery. It was a set of metal surfaces moving against each other under pressure and heat. When those surfaces wore, you restored them. When a seal degraded, you renewed it. Not because you were a mechanic and because you were an owner. And owners understood their machines the way any person understands a thing they depend on and refuse to be helpless about. The people who profit from your engine's deterioration have spent 70 years convincing you that what happens inside your engine is too complex for you to understand, too dangerous for you to address, and too expensive for you to fix without their help. Every single one of those claims is a business model, not an engineering fact. The complexity is real but learnable. The danger is non-existent if you follow the chemistry. And the expense was always the lie. The expense was always the product. Dr. Howard Ellison understood something in 1952 that the automotive repair industry has spent every year since trying to make you forget. Engine wear is a surface phenomenon measured in microns. The chemistry to restore those microns costs less than a cup of coffee. And the only reason that chemistry was ever kept from you is that the people who stood between you and that knowledge had quarterly earnings reports that depended on your continued belief that worn metal is a death sentence for an engine and a birth certificate for an invoice. Now you have the chemistry. Subscribe now, because the next video covers the $3 transmission fluid compound that eliminates the $2,500 flush and rebuild service that every quick lube chain in America has been upselling since 1993. The knowledge does not stop here.
It starts here.
Share this with one person you know who has been told their engine needs a rebuild. One person who is sitting on a repair quote that made their stomach drop. Every share is $3,500 that stays in a real person's bank account instead of funding a repair they never needed on a diagnosis designed to sell them a service, not solve their problem. Every like tells the algorithm that a $2 treatment matters more than a $7,000 rebuild recommended by a service department that generates more profit per square foot than the showroom it is attached to. The next one opens soon. And what is buried inside it will make this feel like the least expensive secret they ever kept from you.